Okay, so hello everyone. Good evening, good morning, and good afternoon, depending where you are. So welcome to the Task Parker class. My name is Jie Xu. I'm from the Chinese University of Hong Kong at Shenzhen. So today I will be the host for this lecture. So Task Parker is an open platform dedicated to fostering academic exchange by connecting researchers, scholars, and professionals across various cutting-edge disciplines. And the Task Parker activities include lectures, technical seminars, and organize many different types of activities to promote knowledge sharing. So we are very happy to have this class at Task Park. So before we introduce the speaker today and the topic, so let me briefly introduce the course series. So we're going to have the course series on fundamentals of channel knowledge map from classical to AI-based methods. So the background is that 6G networks face significant challenges in CSI, the channel seeding information accretion, due to various issues. And on the other hand, the 6G networks has the densest infrastructure, and also it's going to generate a lot of location tagged channel data. So in order to resolve the CSI issue by using the location tagged data, so channel knowledge map is becoming a transformative technology. So I believe Yong will give a more formal definition about channel knowledge map later. So in the course, we try to offer a comprehensive exploration of a CKM, covering the fundamental concepts, technical methodologies for CKM construction and utilization, as well as practical implementation and case studies. So our course includes 4 parts: fundamentals of CKM, CKM construction, utilization, datasets, prototypes, and emergent topics. So the course instructors includes Yong, Professor Yong Zeng. He is IEEE fellow from Southeast University. He will give the first lecture. And also Professor Ri Zhang from National University of Singapore. Myself and Professor Junting Chen from the Chinese University of Hong Kong, Shenzhen. So here is the detailed agenda for the course series. So today, Yong gonna introduce the fundamentals of CKM. And in the second part, we're gonna have 4 lectures. And the part 2 gonna explain the CKM construction from various perspectives, including conventional single processing techniques, generative AI, values radiance field, and also the blend construction. So in the third part, we're gonna talk about the utilization of CKM. So we're gonna have 3 lectures to talk about the predictive communication, network planning, and also long line of sight sensing and localization, as well as the blend utilization for CSI tracking. And finally, in the part 4, we're gonna introduce some implementation aspects, including data sets, prototypes, and emergent topics. So that's a brief agenda for this course series. By the way, here we listed the tentative date for each course, for each lecture, but the exact data may change depending on the schedule. So today we're going to have the first lecture. So we are honored to have Professor Yong Zeng from Southeast University to talk about the fundamental of CKM. So before we start, let me have a brief introduction about Professor Zeng. So Professor Yong Zeng is a chief young professor with a National Mobile Communication Research Laboratory at Southeast University, and also with the Purple Mountain Laboratory at Nanjing. So he received a bachelor and a PhD degree from Nanyang Technology University at Singapore, and worked as a research fellow, senior research fellow, and a lecturer at NUS and the University of Sydney. So Professor Zeng has been listed as a highly cited researcher for 7 years, and he is a recipient of the Australian Research Council, the so-called DECRA, and also IEEE Marconi Paper Award twice, and also the IEEE Communication Society Asia Pacific Outstanding Young Researcher Award and many different paper awards. And Professor Yong has published many papers. He also is the one proposed the concept of CKM. So his papers has been cited by more than 35,000 times. And he has organized many workshops and served as editor for many journals. And he was elected as IEEE Fellow for contributions to UAV communications and wireless power transfer. So without further ado, so let's welcome Professor Yong Zeng to give us a talk. Okay, so Yong, the stage is yours.
Okay, thanks a lot, Jay. Can you hear me?
Yeah, very clear.
Okay, great. Let me share my screen. Okay, so I hope that you can hear my voice and see my screen sharing. So good evening, good morning, or good afternoon, everybody. First of all, thank you very much for joining us. And I also would like to thank Charles Park and Professor Xu Jie for giving me this valuable opportunity actually to give this course. So I'm very happy to give the first lecture of this course. Basically, I'm trying to give the basic concept of channel knowledge map, or CKM. So I will first give some background, trying to illustrate why we need to propose a concept of CKM. And after that, I will try to give a definition of CKM and how it is different from the traditional, for example, the channel modeling or radio map. And then I will give some usage examples for CKM and then some construction problems. So we know that 6G will have some new usage scenarios. For example, from communication, we need to also integrate sensing as one of the usage scenario. And the integration of AI and communication is also one of the important aspects for 6G and also even beyond 6G. So in terms of the capability, we have the sensing related capability. And for positioning, we need to achieve a positioning accuracy about 1 to 10 centimeters. So in order to achieve such very ambitious KPIs, we need to make use of some new technologies. For example, one aspect is that we may shift from the 5G massive MIMO to 6G, so-called XL MIMO, or extremely large-scale MIMO. So in this case, we have a large increase of the antennas, let's say from 64 or 128 antennas to more than 500 or even thousands of antennas. And then we may also have a higher density for the device and also for the base stations. Let's say the device density may increase by an order of magnitude or 2 orders of magnitudes. And in order to achieve intelligence for a number of terminals, let's say for UAV for robots, we will need to have some global or even predictive CSI requirement. For example, for the network connected smart robots, we may need to have so-called communication aware trajectory planning. So all such examples will give us more demanding requirements for channel or the environmental information. But on the other hand, our traditional methods to estimate the channel is mainly based on the pilot-based online channel training. But it has very limited potential, especially if we have certain, for example, simple hardware. Let's say we have a low-resolution ADC, hybrid analog or digital beamforming. So in this case, we have very limited signal access so that we cannot directly access the channel, which makes the channel estimation quite challenging. The similar story goes to some passive devices. Let's say if we have rays or backscattering devices, the channel estimation is a big issue. And we may also have non-cooperative nodes. Let's say the eavesdroppers or the coordinated radio nodes they do not want their channels to be directly estimated. So in this case, this will make the traditional online channel training or environmental sensing ineffective or even impossible to implement. So if we put these two aspects together, on the one hand, we have more demanding CSI requirement, not just about the CSI requirement, but also about the requirement for the environmental information. But on the other hand, for the traditional methods, we have limited potential or limited upper bound. No matter how good we perform under this framework, the upper bound is limited. But how to close this gap? We need to do something new, something innovative. Our basic idea is that we do not really need to do everything online. We can do something offline to so-called exploit the environmental information, that we can achieve a paradigm shift from the conventional environmental unaware wireless networks to the future environmental aware wireless networks. So what do we mean by environmental aware wireless network? So in this paper published about 5 years ago, where we first proposed the concept of CKM, we use 3 very simple examples to illustrate the importance of so-called environmental awareness for wireless systems. So for example, for this first example, we consider 2 UEs that have the same distances with the base station. So if we do not know anything about the environment, we may make a wrong prediction that these 2 UEs may have similar channel strength with the base station. And of course, this is not true if we know that UE2 is blocked by a building. The other example is that if we know the location of the UE, but if we do not know the environment, for the beam forming, we may try to beam the signal directly towards the UE. But if there is a building blocking the signal, then of course the received signal will be very weak. But if we know there is a reflector on the other side, then we can make a more accurate beam alignment before we actually performing the channel estimation or beam sweeping. Similar story goes to this line sight link prediction. If we do not know anything about the environment, we may use some channel modeling to model the line sight link as a probabilistic random event, as a function, for example, as a function of the elevation angle, or as a function of the distance. But if we know the environment to a certain manner, then we can make a more accurate prediction about the line sight link. So this basically shows that if we know something about the environment offline, then we can make a more accurate prediction about the wireless channel so that we can save the resources for the effective data transmission or for the sensing, localization, or navigation. But how can we achieve the so-called environmental awareness? I think the most straightforward manner is to use the so-called physical environmental map. For example, we can download the map from the Baidu, from Google, or from Gaode. Let's say the 3D city map or the building height map. But most of the case, we cannot directly use this map to translate to the wireless channel. We still need some additional information. For example, we need to know the material or the dielectric properties of the environment. And even with that information, we still need to do some very complicated, very costly computation, let's say retracing, if we want to transform the environmental map to the channel map or channel knowledge map. Another technique is so-called radio map, which has been received quite significant attention recently. So radio map basically tries to learn the signal strength distribution at different locations, at different frequency or subcarriers. So for example, if we can use the radio map to find the TV white space, or to find the cognitive radio, the available spectrum, or to find the interference. But radio map or radio environmental map has one limitation, is that it depends on the transmitter or receiver activity. It depends on how much power is used at the transmitter. it cannot directly reflect the wireless propagation, let's say the channel. So because of these limitations for the existing maps, we try to propose a new map that really reflects the wireless propagation channel itself, which is the channel knowledge map. So first, I will give the definition of CKM, and then I will show that CKM is quite different from channel modeling, and we will show the different types of CKMs that we can construct. So what is CKM? If we consider a wireless link, it can be a wireless communication system, or wireless localization, sensing, or even navigation system. So we have a transmitter at a location, let's say QT. So it can be in the 2D location or 3D location. And at a receiver, we have a similar vector to denote the location. So if we put these two locations together, we can find a so-called transmitter receiver location vector Q. It can be, let's say, 4D, 5D, or 6D. So in principle, if this location is the absolute location on the Earth, then actually it reflects to a large extent the local wireless environment. For example, at the location here, we may note that there's a building or there's a tree, and this building and the trees, they keep constant for quite a long time. So this is a valuable information. Of course, we may also have some dynamic environment, let's say the pedestrians or some vehicles. These are the dynamic components for our wireless channel. So in this case, we can define a CKM in a very simple and a very clean manner. It is a mapping from the transmitter-receiver location vector Q. The dimension D can be from 4 dimensions to 6 dimensions, to the channel knowledge vector Z. But in this case, the dimension Z can be quite different. Depends on what kind of channel knowledge we try to learn. So the basic definition of CKM is a mapping from location vector Q to channel knowledge Z. But how can we define this vector Z? Of course, it can be the channel itself. It can be the channel impulse response itself. So in this case, we may use the terminology channel map. But in 2021, when we proposed the concept of CKM, we purposely did not use the terminology channel map because we want to give a more generic definition for this mapping, is that whatever information that is useful to reduce the channel uncertainty, we can put it into the CKM. It does not have to be the channel itself. So in this case, we try to give a more generic definition for CKM, and later on we will show that if we directly try to learn the channel impulse response itself, there will be some big issue in terms of the dimension of the vector Z, and also it is very difficult to generalize or transfer the knowledge across the different devices. So that's why we propose the concept of CKM instead of channel map directly. So let's say if we have a MIMO wireless link with transmitter at a location QT and a receiver at a location QR. So in this link, we have very standard MIMO wireless channel modeling. We can model the channel HT, or the channel impulse response, as a summation of the different contributions from the multipath. Let's say if we have L multipath, then for each path, we may have a delay. We may have an angle of arrival, angle of departure, as well as the path gain, alpha L. So in this case, we may have different channel modeling. It can be stochastic modeling, or some deterministic modeling, or the mix of stochastic and deterministic modeling for this MIMO channel. So for example, from the very classic phase transmission equation, we can tell how the signal strength will decay as a function of the distance. Then we may have the more complicated path loss model, and we may have a very useful relay or racing fading model for the line of sight or non-line of sight links. And then in 3GPP, we may have a GBS or geometry-based stochastic model And recently, we may have an AI-based channel model. So we have developed quite different channel modeling for wireless links. But the limitation of channel modeling, no matter how accurate we developed, they use very coarse information about the environment. For example, for 3GPP channel modeling, we may partition the scenario maybe into 5 or 6 scenarios: the macro cell, urban, macro cell, rural, and so on. And we may also use very coarse positioning information. For example, we mainly use the internode distance. Let's say here in this example, we model the nav site link, the probability of the nav site link only as a function of the distance. So it basically means that I do not care the direction of the UE with respect to the base station. We use the same probability to model this nav site link. So this actually will give us very poor performance if we directly use the channel modeling to predict the channel. So that's why the channel modeling was mainly used for link or system level simulation. But we know that just like there will be no leaves in the nature are identical. Similarly, there will be no locations even in the same environment will have identical propagation characteristic, even stochastically. So in this case, if we want to use the modeling or some AI model to predict our channel more accurately, we need to use some information about the environment, about the location. So this is basically the paradigm shift from the conventional channel modeling, where we do not really consider about the location information, right? And we can say whenever we give the channel modeling for HT, we do not consider the location. But for CKM, based on our definition just now, we actually will provide the so-called location-specific channel. So in this case, we put QR and QT, so that this channel matrix or the parameters is a function of the location vector. This will basically give us the definition of CKM. So if we consider a practical environment, let's say here, if we use the conventional channel modeling to predict the path loss, we will have this kind of result. But if we use the more accurate, let's say retracing, so that we can have a location specific instead of only distance specific channel gain prediction, we can actually make a more accurate prediction, and the accuracy improvement is actually is huge. So this basically shows that from channel modeling to CKM, we can achieve much more accurate prediction about the channel. So if we compare the channel modeling and the CKM, we find that their usage will be quite different. For CKM, we try to support the so-called environment-aware communication sensing localization, so that we can make use of the predicted channel to facilitate or improve our performance. But for channel modeling, it was mainly used for simulation or performance evaluation. And also, we try to make more accurate use of the environment and the location information. But actually, there is a misconception about CKM. When we discuss this CKM concept with some researchers in academia or from the industry, their question is that how accurate can you construct a CKM? If it is not accurate enough, then it is useless. But what I want to say is that we can have very flexible CKM. Even the CKM is not accurate enough, we can have very flexible channel prediction from the very coarse prediction to the accurate prediction. So it should be a smooth transition from the conventional channel modeling to the CKM-based channel prediction, right? So we will illustrate this point more later on. So with this definition, we can actually make this Z, or the channel knowledge, more concrete. So it is a mapping from Q to Z. But depends on what we put into this vector Z, we may have channel map. we may have a channel gain map or channel path map. So I will discuss each of these types of maps in the following. So the first channel knowledge map is so-called a channel map itself. So it basically tries to learn the location-specific channel impulse response. So this is a very ambitious goal. So in this case, let's say this is our channel, and if we discretize the delay based on certain bandwidth, based on certain resolution, we can obtain the channel matrices for each delay type. So in this case, if we put all the channel matrices into one vector, we may have a very huge vector. So for example, for each type, the dimension of the matrix depends on the number of transmit and receive antennas. And how many such matrices do we have? It depends on the bandwidth, depends on the delay spread of the channel. So let's say if we have 64 antennas at the receiver and 8 antennas at the transmitter, and if our bandwidth is 100 megahertz with a delay spread of 1 microsecond, this dimension for the vector Z to store and to learn the channel impulse response is huge. It is more than 10,000. And keep in mind that this is only one single location vector Q, the dimension for one single location vector Q. Of course, we can use some compressive sensing or make use of the sparse property to further reduce this dimension. But again, if we want to learn the channel impulse response or the channel map itself, then the dimension is impossible to learn. It is very difficult to even to store this this vector. But of course, the channel impulse response has the rich information for the downstream tasks. Okay, so another limitation for this channel map is that this channel matrix depends on how many antennas we have, and also it depends on the bandwidth of the system. So it basically means that if we learn one channel map for one set of antennas, but then the same channel map cannot be used by another set of antennas because this matrix will be different. So if we directly learn the channel map, then it is very difficult to transfer the knowledge we learned for one set of devices to another set of devices. So this is another big limitation. So another channel knowledge map that we can define is so-called channel gain map or CGM. Actually, this is one of the most studied CKM. So the basic idea is that if the dimension of the channel matrix itself is too large, then what if we only care about the channel strength? Let's say for each delay type, we only want to know how strong the channel is or how strong the signal is. Then we only care about the norm of this channel. So in this case, we can reduce the dimension significantly. Let's say if we have only 100 delay types, then we only need to learn 100 dimension for this vector. But of course, if we do not care about the delay, we sum the channel strengths for all the delay types, then we only need to learn for one dimension. Let's say like this. So this is actually one of the most commonly studied channel gain map. That is one dimension for each location. We have one dimension will give us the channel strength in, let's say, in dB. Of course, this will be very easy to learn, and it is very popular. But the main limitation is that the information or the knowledge for this CGM is quite limited. It can only support a very limited downstream tasks. For example, we can use this maybe for network planning, but let's say for beamforming, for sensing, for localization, then this map will have very limited usage. Another very popular, a very promising map, I think, is so-called channel path map. So the basic idea is that instead of trying to learn this matrix, we try to learn the multipath parameters of those significant multipaths. Let's say we only try to learn the 5 most significant multipath. So in this case, each path will have 7 parameters: the path gain, the angle, and also the delay. So in this case, if we try to learn 5 of the path, then in total, we only need to learn 35 dimensions. Another very important advantage for CPM is that we can establish a global coordinate, let's say for the angle of arrival, so that this Z only depends on the environment. It is independent of the number of antennas at the transmitter or receiver. It should be independent of the orientation of the antenna array, because we try to use the global coordinate system to build this CPM. So what is the advantage for this kind of definition? First of all, as compared to the channel map, the dimension has been reduced. And it's actually complete. Can use this channel path map to reconstruct the channel, or at least to approximate the channel if the number of L is large. And another important feature is that, as I mentioned just now, this Z should be independent of the device. It is independent of how many antennas we have. It is independent of the orientation of the antennas. It is independent of the how much power you use. So it only depends on the wireless environment. But of course, the limitation or the challenge is that it is more demanding for the data collection. For example, we want to build a global coordinate system for the angle of arrival or angle of departure. But if we compare the different channel maps, channel knowledge maps we discussed so far, for the CPM only depends on the environment. But for channel map, channel gain map, or radio map, it not only depends on the environment, but also the transmitter or receiver. So for CPM, since it only depends on the environment, then we can build a CPM so-called that can be shared by all devices and also by all tasks. Let's say we call it a CKM for all and all for CKM. So what does this mean? If we build a channel knowledge map that depends on the number of antennas, depends on the devices, then it basically means that let's say a channel knowledge map that is developed for the smartphone cannot be shared by, let's say, by a vehicle or by a UAV, because they have quite different number of antennas or the different capabilities, right? And our channel knowledge map, if designed to be dependent on this kind of parameters, then it is very difficult to transfer the knowledge across the different devices. But for CPM or for CKM that is only dependent on the environment, then no matter it is for smartphone, for a vehicle, or for a UAV, we can share the common CKM. And this is called the CKM for all devices. And on the reverse side, for the device, we can connect the data. Then all the data can be fused together to construct one common CKM or CPM. So this is called all for CKM. I think this is quite important because if we cannot build one single CKM, then the concept about CKM or whatever map we can propose will be very difficult to build in practice, because we have so many different devices, and each device may have different configuration. And if we want to build one map for each of them, then I think it is impossible. So another technique, as I mentioned just now, is radio map. Radio map is quite different from CKM in that it basically tries to learn the location-specific channel gain or the signal strength. So it depends on how much power we transmit for each transmitter and which transmitters are activated. So another important difference between CKM and the radio map is that CKM is a function of both the transmitter and the receiver locations, but radio map is only a function of the receiver locations. Of course, there are different research groups. They may mix the usage of radio map, channel map, or channel gain map or CKM. But here in this course, I try to make the distinction from my perspective, and I try to say that they can be quite different. And if we can build a CKM, as we mentioned just now, we can make a huge difference for the wireless networks. So a little bit of the history. Actually, the concept of radio map or the terminology of radio map was proposed more than 1 century ago in 1920. But the initial concept of radio map is quite different. It basically gives the locations of the broadcasting stations. And then in 2005, we have channel map, and then we have channel gain map, REM, or channel shadowing map, or engineering radio map. And then in 2021, we propose a CKM. And the key difference is that, as we mentioned, we try to build a CKM that can be shared by all devices and by all tasks. And also, we try to, from the very coarse or large-scale geographic distribution on signal strength to the very fine-grained location-specific channel knowledge, which has much more rich information about the propagation environment. So if we compare the different CKMs and the radio map, we can find that the knowledge Z, the vector Z, can be quite different. And of course, the dimension J can be quite huge. Let's say here, it can be very huge. And also, for another aspect is that whether it depends on the transmitter and receiver antennas or the transmitter power, whether we can transfer the knowledge from one device to another device. And we found that the CPM we discussed just now is a quite promising CKM, so that we can transfer across all devices. So actually, hopefully, we have given a very clear definition of CKM, and hopefully we can say that it should be quite different from channel modeling, from channel gain map, from radio map, and if we can build a CKM that can be shared by all devices, and I think it can make a big difference. So now, where I will try to, let's say we have built the CKM as we discussed just now. How can we make use of the CKM to support the so-called environmental aware communication, sensing, localization, or navigation? So here I only give a very high-level introductions for the usage scenarios for CKM. And for the subsequent courses, we will give more detailed technical discussions for CKM, for the usage of the CKM. So I will give 3 examples: CKM for communication, for low altitude UAV, for ISAC. So based on the definition of CKM, we need to first try to find a way to find the location. It can be an absolute location, but of course it can be certain so-called virtual location. We can use, for example, the satellite, let's say the GPS or BeiDou, to localize our device, or IMU, vision-based localization, radar, Wi-Fi, LiDAR. So we have so many localization techniques. And what is important is that many localization systems are so-called free. So what do I mean by free? Free localization system means that it does not have to use the wireless resources. Let's say if we want to use CKM to support wireless communication, then if we use a satellite or IMU or vision-based localization, they do not require you to spend to use extra device or extra spectrum or extra time to do the localization. These systems are already in our devices, so why not we use it, right? So they are free localization systems. So with this, we can query our CKM we discussed just now to find the prior information for the channel knowledge at this particular location, the transmitter location and the receiver location. So how can we use this location, this kind of channel knowledge to support communication, sensing, localization, and navigation? So when we first proposed the concept of CKM, our idea is to support communication, let's say to do channel state estimation. But actually, it can also be used for sensing, localization, and navigation because they all dependent on the wireless channel. So let's say if we try to plan our trajectory for a UAV, before we actually reach the location, we cannot apply the traditional channel estimation to estimate the channel. So in this case, we need to do some predictive channel estimation or channel prediction so that the channel knowledge map will be quite useful. Another scenario is we mentioned just now, if the other node is non-cooperative, then it is impossible to do the conventional channel estimation, let's say for the eavesdropper. And another possibility is that if we have large number of antennas, we can, of course, we can do some channel estimation, but the cost will be very huge. The delay and the wireless resource we need to use for channel estimation will be unaffordable. Or of course, if the hardware or signal processing is very limited, let's say for RAIs, for backscattering devices, then the channel estimation will be quite challenging. So in this case, we can make use of the CKM to predict the channel. So if we have this kind of knowledge, we can support our communication. Let's say we can use it to reduce our beam alignment overhead. We have a transmitter and a receiver try to find the best possible beams at the beam code book. So as our number of antennas get very large, our beam will be very narrow, and the number of beams will be huge. Then the combination will be a very large number. Then the traditional beam alignment will be very ineffective. But if we know something about the environment, let's say if we know the building like this, we can reduce the beam sweeping overhead to support the beam alignment. And of course, we can also use CKM to enable the channel estimation. So let's say if we know the more accurate probability distribution about this location-specific channel, then we can make a more accurate channel prediction. So we have some initial works on this kind of CKM utilization. For UAV, we can make use of the CKM to plan the trajectory, right? For example, the traditional trajectory planning is mainly for collision avoidance. We do not try to crash the UAV with the building. Another important aspect is that we try to make sure that as the UAV moves along the trajectory, we can always maintain a very good quality connectivity with the base stations. So in this case, we need to know the wireless environmental information. So CKM will provide us such information. And another possibility is that if we want to use a base station to track the UAV in a complex environment, let's say in the city environment, the nav site link may be blocked. So the sensing signal or the radar signal maybe sometimes is reflected by the UAV, but in some other scenarios, they are reflected by the building. So in this case, we need to first make a judgment whether this signal is from a UAV, from a target, or it is from the environment. So in this case, we can make use of the CKM to enable non-nav site tracking or nav site or non-nav site discrimination, so that even in the complex environment, we can track the UAV. CKM can also make combined with ISAC. For example, for this ISAC scenario, the base station tries to communicate with this UE, and simultaneously, it tries to use the sensing signal to sense this target, to localize this target. This problem is quite challenging if the direct link between the base station and the target is blocked. So we can only rely on the non-site link. This signal will be reflected by the building, for example, and then it will be echoed by the target, and then further reflected back by this building. So this will be a very challenging scenario. If we do not know the environment, then it is very difficult to localize this target. But if we have some environmental information, let's say CKM, then we can enable this non-nav site sensing localization. And the key point is that we do not need to build one separate CKM for this sensing. We can reuse this CKM for the communication to achieve the non-nav site sensing. So in this paper, our title is that you may use the same channel knowledge map for non-life cycle sensing and communication. And another aspect is that for the clutter rejection. So let's say if we have a ISAC scenario, then this reflected signal will cause interference or clutter to this sensing signal, because this reflected signal does not go through from the sensing target. So it will cause interference to this sensing task. The challenging scenario is that if this reflected signal from the building is much stronger than this echo signal from the targets, then it will be very challenging to estimate the locations of the target. So how to remove the clutter signal is a big issue. So if we know CKM, let's say if we can learn the multipath angle of arrival for this building, then we can remove this signal even before our radar signal processing, so that we can make a more accurate radar signal prediction. So this is basically a CKM enabled clutter rejection. It gives us a new DOF for clutter rejection. So for CKM and ISAC, we actually have a so-called mutual enhancement relationship. So on the one hand, if we have ISAC, we can sense the environment, we can sense the locations of the terminals, then this kind of information will be very useful for us to build a CKM. So on the other hand, if we have CKM, then we can provide the so-called environment-aware ISAC to improve our communication and sensing performance. So if we combine CKM and ISAC, we can achieve the effect of 1 + 1 greater than 2. So that's why in this case, we built a prototype, a very simple prototype for CKM ISAC. The basic scenario is like this. We have an ISAC base station with a transmit antenna array with a phase array, and also with a receive antenna array. This transmitter antenna array will send one single OFDM signal. It carries the information to this UE. And a part of the signal will be received by the antennas of the UE for communication signal processing, let's say to transmit the video. And the other part of the signal will be reflected by the environment, also by the UE itself, so that this receive antenna can make use of the reflected signal to sense the environment and also to sense the location of the UE. For example, the angle of arrival, the direction of the UE, the distance, and the velocity of the UE. So in this case, we achieve the truly ISAC by using one single waveform and one set of antennas. And what's more, the ISAC result can be used to build the channel knowledge map. It is quite useful to build a CKM, so that this CKM can be utilized for subsequent localization and communication tasks. So let's say if we consider this practical environment, the UE moves in this non-life site environment, then the base station will sense this UE and also the surrounding buildings. We can always track the UE, even in the non-life site scenario. And as the UE moves in this environment, we found that we know some knowledge about this wireless link. Let's say the color will change. Let's say we can learn the channel strength, the angle of arrival, and so on and so forth. So in this case, we can make use of this information. Let's say next time the new UE comes in, then we already have the information so that we can make more efficient communication or sensing tasks. So this is the very initial prototype for CKM and ISAC. So here we only give a very high-level overview for how we can make use of CKM to support communication, sensing, localization, to support ground vehicles or UAVs. But the big problem is that how we can construct a CKM. For CKM construction problems, we have a few lectures dedicated for CKM construction. Here, I only try to kind of formulate the problem. So first question is how to represent the CKM. And then what kind of CKM construction problems do we have? We consider two categories, the so-called non-transferable and also transferable CKM construction. So let's try to come back to the definition of CKM. We define the CKM as a mapping from location vector Q to a channel knowledge vector Z. So we know what should be our Q, we know what should be our Z. But another issue is that, how about this block? How about this block? How do you mathematically model this CKM? Actually, there are two approaches. The first one is that we know a mapping is essentially a function. We can use a deterministic function from Q to Z. You give me the input Q, I give you an output Z. So this is the deterministic mapping. Another possibility is the so-called stochastic mapping. You give me Q, I do not directly give you Z, but I give you the distribution of Z, the possible distribution of the Z for this particular location Q. So there are two approaches. So let's say if we consider the so-called deterministic mapping, then the CKM construction problem is basically to try to find this function. So if we use f theta of Q, where theta is our parameters. So let's say in this case, we can first assume certain mathematical model for this mapping from Q to Z. Let's say for the path loss, we can select our path loss modeling with parameter KTDB, also the path loss exponent n. So in this case, it's a function of Q in terms of the distance. The norm of the Q means the distance from this location to the base station. So in this case, we can use some learning technique to find this parameter theta. So in this case, of course, we need to collect some data. Let's say we have certain location and knowledge paired data Qn and Zn. And then based on this data, we can do some training or some curve fitting to minimize our predicted channel knowledge versus the data in the data set. Let's say the loss function is the MSE. For this case, this theta, we can use a very, I think it's a least square problem. We can find the theta for this particular channel gain map or path loss modeling. Actually, this is also the standard technique for channel modeling. We can collect the data and find the most suitable set of parameters for this set of data. But this kind of model-based approach, we need to find the mathematical model. Then, of course, we have some model for the path loss of even for the angle of arrival. But for the more complicated channel knowledge, it will be very difficult to so-called handcrafting the math model. So in this case, why not we use the so-called model-free approach? Our target, remember that, is try to find the mapping from Q to Z. And we know that if we do not know anything about the environment or about the math model, we can use the AI method to train a neural network, let's say based on the data Q, to train a neural network for this model or for this mapping. Because in principle, a neural network can approximate any linear or nonlinear function. So this is one of the fundamental theory for AI, for neural network. So in this case, we can train a neural network, let's say a deep learning based method or deep feed forward neural network. The input is Q, the output is a prediction of Z, and then we can minimize the loss function. This is the standard supervised learning problem. So we can use a back propagation to find the weighting coefficient theta. So this is quite standard. So one example is like this. In this 2021 paper, this is a ground truth CKM based on the ray tracing. And this is the CKM or channel path map or the channel gain map based on the path loss modeling, but for the model-based approach. And this is the deep learning-based approach. We can find that if we do not restrict to a certain model, we can make a more accurate channel gain map. So far we discussed how we can map a channel allocation vector Q to the channel knowledge vector Z in a deterministic manner. And also so far, we give the modeling for the so-called time invariant channel, MIMO channel modeling. Of course, the wireless channel is time varying in nature. Even, of course, the time variant can be due to the mobility of the UE or the transmitter or the receiver. But even for the fixed UE location or base station location, the channel is time variant because the surrounding environment can be time variant. For example, the vehicle, the pedestrians can also affect my channel. So even for the fixed transmitter receiver location Q, we may observe quite different channel knowledge at different time t. So in this case, if we simply model the CKM as a deterministic mapping from Q to Z, we cannot reflect this dynamic environment, right? So in this case, the deterministic channel modeling or CKM, although it is quite simple to learn, it cannot reflect the dynamic environment. In order to solve this problem, we actually need to represent the CKM in the so-called as a conditional PDF. Like this, instead of giving predict Z, we predict the location specific or location conditional distribution of Z. Let's say if at this location Q1, I will give you one distribution for this Z. And at another location, the distribution can be different. Of course, the deterministic mapping is one special case of this conditional PDF. If the PDF is a data function, we will degenerate to the deterministic mapping. So if we represent CKM in this way, we can have a more generic CKM representation. And what is more important is that this kind of CKM representation can handle the dynamic environment. So it does not give one single value, it gives us the distribution. So the key question is that how can we learn this distribution, the location-specific distribution? So again, there are two approaches. The first approach is model-based. The second approach is model-free. So for model-based approach is that we do not directly assume certain model for the deterministic mapping. We assume certain model for the distribution, for this location-specific distribution. For example, a very simple distribution model is a Gaussian-based model. But the key point is that the modeling parameter depends on this location Q. So for Gaussian, we only need to specify the vector, the mean vector and the covariance matrix, and then we have the full PDF. So in this case, for each location Q, we may have a very unique mean vector, also the covariance matrix for this channel knowledge Z. So in this case, the CKM learning problem will reduce to learning the location-specific modeling parameters from Q to X, and this X includes our mean vector of this Z, also the covariance matrix of this distribution for Z. And we found that in this case, the dimension of X may be further increased. For example, if we use a CPM, and then the dimension, let's say for each of them, in this case is 7 parameters. For each of Z, we have 7 parameters, and then the mean of this vector will be have dimension 7, and the covariance matrix will have dimension 7 by 7 will be 49. Of course, the covariance matrix have some symmetric property because it should be a positive semi-definite matrix. So then we can reduce the dimension of this X to 35, but it is still a huge number. But if we assume certain independence, then the dimension of this X can be further reduced to 14. And as compared to the channel map itself, which is more than 10,000 dimension, this 14 is much, much smaller. So in this case, we can learn the similar mapping from Q to X, let's say with a similar approach with the supervised learning. But of course, Gaussian PDF is a very simple PDF. Our ground truth distribution may not be Gaussian. Then in this case, we may use more complicated model, let's say mixed Gaussian. We can use a mixed Gaussian with I modes. In this case, we have more parameters, more location-specific modeling parameters to learn. Let's say this is one example for the 2 modes Gaussian. Then we need to know to learn the mean and the covariance matrix of each of the Gaussian mode, and also the mixing probability. But again, mixed Gaussian may also not be the ground truth distribution. So in this case, either we use a Gaussian or mixed Gaussian, it can be far away from the ground truth. Then in this case, can we use so-called model free? We do not pre-assume any distribution for this so-called location-specific distribution. Can we mainly only use the data to learn this distribution? The answer is yes, we can. And this is exactly the framework for the generative AI. The basic idea for generative AI is to learn the distribution from the data without assuming any prior assumption for the distribution. And we will talk this, I think, maybe 2 weeks later before the holiday. So far, let's try to give the basic problem formulation for CKM construction. So what do we really mean by CKM construction? The basic setup is like this. Let's say we have collected certain data. Of course, we need data, whether it is an AI-based method or without using AI, we need some data. Data can be have a location Qn and the channel knowledge Zn. And we may connect the data from a certain area Q1. And then we try to build a CKM maybe for another environment or area Q2. And of course, we need to know some environmental knowledge. This knowledge, this environmental information for this Q2, where we try to build the CKM, can be incomplete. For example, this kind of environmental information, maybe our point cloud, it can be a very, very low resolution picture for this environment, or it can be some very sparse measurement of some channel knowledge. So with this kind of information, it is impossible to use our traditional ray tracing or some Maxwell, by solving Maxwell equation to find the channel knowledge for this Q2. So in this case, the basic idea is that we try to mix the use of the data set and also the environmental information for this CKM where we want to build to actually build this CKM. So this is the basic setup. We have data set. The data set can be connected from another area. And we have some environmental description of this CKM area. With certain CKM construction algorithms, we try to build a CKM for all the possible locations Q in this area, which is basically the conditional PDF for Z. So we have 2 scenarios. The first scenario is that the data connected area is the same as the CKM construction area. Let's say we try to build a CKM for the Southeast University campus, and we also collect sufficient data in this campus. So this is one scenario. And we call this construction problem as a non-transferable CKM construction, because we only make use of a CKM data collection in this area, and we only construct the CKM for this area. So the algorithm will be likely to be non-transferable to another area or to another city. The more challenging scenario is that if Q1 does not equal to Q2, so we try to build some algorithms that can be transferred. The knowledge can be transferred from one location to another location, from one city to another city, let's say from Nanjing to Beijing. So this will be more challenging and will be more useful. So in this case, for the first scenario, if the CKM will be built based on the data set for the same area, actually the problem is quite straightforward. And most of the CKM techniques in the literature actually considering this scenario. So how can we build a CKM for this kind of scenario? Actually, we already discussed the technique, the so-called model-free or model-based approach. So depends on whether we try to use a model-based approach. We can first determine the model, let's say the Parsons model, and then based on this data, we do some data processing and then do the model training based on the technique we discussed just now. Either we use a AI technique to train the Q to the channel knowledge Z or X. So this is the supervised learning problem. But the more challenging scenario is that the data set is connected in this area for this city, and we try to build the CKM for another city. How to deal with this more challenging scenario? And the question is, maybe is it possible for us to use the data collected in one area to construct the CKM for another area? If so, how do we transfer the knowledge learned in area Q1 to another area Q2? And how to specify the environmental information for Q2? So the key idea is that we can make use of AI, more specifically generative AI, try to learn the joint distribution of the high-dimensional data that is independent of the absolute location, but only depends on the relative locations. So in this case, we can formulate the CKM construction problem in this transferable learning problem as a so-called inverse problem. X is a CKM for the different pixels in these locations. In this area, we try to construct X. Y is our observation. Let's say here is our completed CKM. We try to build, but we only observe part of the signal. Let's say this part is blocked, is masked. How can we, based on the observation of Y, to infer this ground truth X? This is a so-called ear-posed inverse problem because we do not have any information about this area. Then there are infinite possibilities of this for this X that can map to this Y. So how can we make use of the knowledge about this probability distribution of X to make a more accurate prediction? So in this case, we need to make use of the so-called generative AI. The basic idea is that if we know the prior distribution of X, now this X is not the parameter X we discussed just now. It is a ground truth channel knowledge map X. It's a joint distribution. It's a high-dimensional distribution. For example, if we want to build a CKM for 100 pixels by 100 pixels, then this X, the dimension will be 10,000 dimensions. It's a high dimension. It is very difficult to use a traditional modeling approach to model this distribution. And fortunately, in the generative AI, we can use the generative AI approach to learn the distribution of this PX. If we know more accurate prediction about this PX, we can solve this inverse problem more accurately. So this will cover a set of CKM construction problems. For example, CKM denoising. If our measurement has noise, we can remove the noise. CKM impeding. If we can only access part of the locations to measure the channel knowledge, then we can make use of this distribution to recover this removed part, or CKM super resolution, or even CKM generation, so on and so forth. So we will cover this from in lecture 3. So so far in this first lecture for CKM course, I gave the definition of CKM. I try to distinguish CKM from conventional channel modeling from radio map, and my vision for CKM is so-called CKM for all devices, for all wireless tasks. For localization, sensing, and communication, we may use the same CKM. For UAV, for smartphone, for vehicles, for the ground vehicles, we should use the same CKM. And all these devices should contribute data to the CKM construction. So in this case, maybe we should say CKM is a foundational model towards the digital twin. I'm not sure. And the channel map or channel gain map or radio map do not meet this above vision. But the channel path map, because it only depends on the environment, it is independent of the transmitter or receiver, so it is quite promising towards this vision. And of course, we can develop CKM construction algorithms for the non-transferable. It is quite straightforward. But for the so-called transferable one, if we learn the knowledge in city A, how do we transfer to another city B? So it is quite challenging. And we will discuss this in lecture 3. And another issue is that the environment can be described by vision, sensing, lidar, or even language. So how we can make use of multi-modal information to construct a CKM or to make use of the CKM, where I think it will be quite promising. Okay, here are some major references for the tutorial and magazine. Here is the first paper to propose the concept of CKM. And then here in 2024, we provide a tutorial for CKM. And we also try to build some CKM data set. We call it a CKM ImageNet. And we will discuss this data set, I think, after the holiday. And we have the CKM construction problems and CKM utilization for different tasks for the UAV trajectory planning, for the hybrid beamforming, and also for the millimeter wave beam alignment. Here are some very simple prototypes for CKM and also for ISAC. And some of the videos are available online. I think in Bilibili and also in our WeChat video channel. And of course, the CKM are also discussed or researched by different research groups. Here are some non-comprehensive lists for CKM research. And with that, I would like to end my talk. Thank you very much.
Okay, thanks, Yong, for the very comprehensive talk about the fundamentals of CKM. So we got a number of questions. So I think, yeah, your talk is very attractive. So yeah, the first question is about how to use CKM in a dynamic environment. So the audience asked about the UAV path planning, right? Does CKM allow us to predict the channel quantity for yet to reach locations? And how does the proactive resource allocation handle the instantaneous channel fluctuation caused by sudden changes like the UAV altitude?
Yeah, thank you very much for the question. Yeah, I think this is indeed a very important question of CKM for dynamic environment. So actually, when we first proposed the concept of CKM, myself do not have the very clear picture because we just map the location to certain kind of channel knowledge. But as we go deeper to the research, some practical research problems and also the discussions with a number of people from the industry and from the academia, this is really indeed a very big problem. So that's why in this talk, I try to promote the concept is that we do not have to model CKM as a deterministic mapping. We must use the so-called this conditional PDF. The key idea is that no matter it is for communication, sensing, or localization, as we mentioned, the environment is dynamic. So as long as we do not fix the deterministic mapping, what we learn is the long-term distribution. But it is different from the channel modeling. This long-term distribution is very specific to this location. So even the dynamic environment is the environment change. For example, you mentioned if the UAV suddenly changes the location, change the trajectory, change the height, and this kind of location information is also the additional information we can make use as the input to our CKM. Of course, we cannot purely rely on this channel knowledge predicted by CKM to do the resource allocation. We may also need additional, let's say, 1 bit or a little bit of pilot training. But this training, this online or sensing or online sensing will be very light because we have very specific narrowed the PDF. For example, if without this CKM, our variance of the channel modeling will be huge. Let's say we have large variance. But with CKM, after the learning, maybe we have this kind of distribution. Then it will actually give us very rich information for our subsequent sensing or channel estimation because we have more accurate prior knowledge about this location information. And then the key idea is that for dynamic environment, we should not mainly only use the CKM to predict the accurate channel. That is impossible. We still need to combine the online training or sensing, but that will be very light because we have very narrow or very specific conditional PDF. so that we can reduce the training overhead, we can reduce the training delay for the subsequent resource allocation or trajectory planning. That is my main idea.
Okay, thanks. Yeah, we also get several questions on the relation with the relation of CKM with other techniques. So, so one question is, so nowadays we have many different types of antennas, like fluid antenna, movable antenna, and pinching antennas. So in this case, right, if the antenna gonna change dynamically, right? So how to construct the channel map? I think it's related to the previous one, but maybe
Yes.
the antenna movement, right? So the scale of the antenna movement may be much smaller as compared to the UAV change.
Yes, yes. Yeah, I think that is also a quite important issue. I think we need to consider this issue from two aspects. The first aspect is that whether this kind of new antennas can contribute the data for our CKM construction. Another aspect is that whether our constructed CKM can be utilized by this kind of antennas. I think my understanding is that if we define our CKM like this, only depends on the environment. It is independent of the antenna. It is independent of how we make use of the antenna. Then the answers to the above two questions are positive. So no matter what kind of antenna we use, whether it is a fluid antenna, movable antenna, or hybrid beamforming antenna, or massive MIMO, XL MIMO, or even single antenna, then in principle, as long as we define the CKM or we represent the CKM that tries to learn the propagation channel itself, let's say the multipath angle of arrival in the global coordinate system, then we should be able to make use of the CKM to support our, let's say, the antenna movement, also to support the fluid antenna resource allocation. I think that is also a very promising use case, which I didn't mention in my talk for CKM, because for CKM movement, for fluid antenna or movable antenna, before we actually move to the location, maybe we should make use of prediction technique to predict what if after we move to that location, how the channel knowledge or channel will look like. So CKM is one of such a possibility. So that's why I think it is very important to promote the concept of the CKM for all, and all for CKM, not just for all antennas, for all devices, but also for all kind of wireless tasks. Yeah, that is my understanding.
Okay, great. So this is another question about how to transfer CKM over different scenarios. I think at the end of your talk, right, you briefly mentioned that, and you will have a detailed explanation in next lectures. But I think you can elaborate some key ideas, right? Because the audience asked, can the trained CKM be transferred to new scenario maps or new channel models? For example, can the urban map be transferred for indoor or near field channel transfer to or far field? So what is your view about it? Yeah.
Yeah, that's really a very good question. I think, let's say for the specific question, can outdoor channel knowledge map be transferred to indoor? Actually, for this kind of scenario, I'm not quite sure, because let's say if we only use the outdoor channel knowledge data to train a CKM, and then we directly use this knowledge for the indoor. From my understanding for the AI transfer learning, maybe it is quite challenging. I would not say impossible, but the key idea is that if we can see some similar environment, but not exactly the same, maybe there is certain possibility. My key idea for this transfer learning or this transfer CKM construction, the key idea is that as compared to the first case, we use the data connected from the same environment to construct the CKM. So in this case, we can use the absolute location. Then In this case, it is very difficult to transfer because for this location, the environment is very specific. As we mentioned, there will be no two locations that have exactly the same environment. But the joint distribution of the data will share some similarity. So the key idea is that instead of learning the absolute mapping from Qn to Zn, we try to remove this location dependence Qn for our subsequent learning. Because if your learning is based on this location, absolute location Qn, I do not think it is very easy to transfer. Because the location at Nanjing and Beijing and Shenzhen, they are specific, they are quite far away. How can you transfer these locations? Their environments are quite different. So my key idea is that first, we need to find a way to process our data set so that this Qn will be gone. We will replace this Qn with some other tag, which we call relative location. Let's say we will replace this Qn with, we consider 2 points. Then the relative distance, whether it is 1 meter or 2 meters, whether it is to the north or to the east of this location. Then these 2 points will have joint distribution for the channel knowledge Z. So we need to consider the joint distribution at different locations, and we try to learn this joint distribution, which is basically this X. X is not just one location. It is a set of locations, let's say 100 locations, and we try to learn this joint distribution. And this joint distribution after the CK, after the data set, we can construct a large number of this kind of joint distribution, which is basically this kind of image. And this image is independent of the absolute location. And we can transfer this kind of CKM construction problem to the image distortion, image reconstruction problem. And we can share the similar idea. So yeah, that is the basic idea. And I think if we wanted to transfer this kind of knowledge, at least statistically, we should have some statistical signal X from the similar distribution so that we can transfer this kind of learning. So the question is whether we can transfer from near field to far field. The key point is how do we represent the signal, the map, so that there is a link between them for the transfer. And also for the outdoor and the indoor, we have similar issues. I'm not quite sure, but I think it will be very important topics to further study. Yeah.
Yeah, exactly. So, so the other question is about the scalability of the CKM, right? So, so some audiences are interested in the CT scale map. This means that the scale is quite large, and in this case, accuracy is another issue, right? So how to construct a highly accurate CKM in a large scale scenario is quite critical. So and also another audience asked about the use of satellite communication, right? For example, the low Earth orbit satellite-based communication network. So CKM may also be used, right? So in this kind of large-scale scenarios, what is the challenge for constructing CKM, or what is the main scenarios CKM can be used?
Yeah, thank you for the question. Yeah, for the first question, yeah, exactly. CKM, if we try to make full use of the CKM, of course we need to have at least a city scale. City scale CKM, of course, it is quite challenging, but we should think of the problem in this way. We do not really try to have one single CKM for the whole city. Let's say for the base station centric communication, right? We do not try to build one single base station for the whole city. That was for 1G, for the first generation, yeah, we try to build one single big tower for the single city. But for nowadays, right, we have many base stations. A base station maybe have a coverage about 200 meters or 500 meters. So we try to build, let's say each base station may have a CKM for its own coverage area. So this basically shows that it is kind of a hierarchical structure. we maybe have one CKM at the edge, at the stair edge, at the base station tower. Maybe we have some common information, exchange information in some cloud or in the fog area, so that we can have some exchange of the CKM between the base stations. So I do not think we should build one single CKM. If we partition the CKM for the base station centric idea, then that should be quite straightforward, especially then we have the so-called concept of AI RAM. The base station may be just an AI computer or AI computing resource. Then we can naturally use the base station to construct a CKM. And then we only exchange the necessary information among base stations for the CKM. So this will make it more scalable to build a city-wide or even national-wide CKM. And for satellite communication, I think the similar idea will also go to CKM, but I do not use the satellite as a use case because, of course, I have very limited knowledge for satellite communication. Another question we may try to ask is whether satellite communication really face any challenge or any bottleneck, for example, in terms of the channel state information, CSI acquisition or channel training, or in terms of the complex environment for sensing or localization. If so, of course, we can make use of the similar idea to construct a CKM for the satellite to ground links. But the issue is that how can we collect the data, and also the high Doppler issue may be need to be considered for CKM construction. I think it will be a very interesting problem for applying CKM to satellite. I think maybe there should be issues that we do not know yet, and it is deserved to have an in-depth investigation.
Okay, yeah, quite insightful. So I have last two questions. Okay, so I see a lot of questions, but I will summarize them into the last two questions. So one is related to AI. So you also mentioned about AI, right? So now AI is everywhere. One question. So I noticed that you mentioned CKM as a foundation model, right? And the question asked, so how? Sorry, let me check. Yeah. So how to use? So actually, the question asked, is there any kind of a foundation large models for CKM? And this is another related question. Ask, so how can the large language model play a role in CKM, or what kind of problems can be solved by integrating LLM and CKM? Yeah.
Yeah, thanks for this question. These two questions are actually we discussed quite a lot in my research group. The first question about the foundation model, actually, we also try to say whether CKM can be used as a foundation model. Of course, we are very familiar with the foundation model for the language foundation model, for the vision foundation model. My understanding for the foundation model is that it can be used to support multitasks. For example, here I try to say it is a foundation model because I try to promote a CKM to support communication, sensing, localization, try to promote the CKM for all devices. So from this perspective, maybe we should call it the foundation model. But I'm not sure whether maybe different people may have different interpretation. And whether we already have a foundation model, we try to make this effort, but we do not have any very mature model to release, but I think it is quite promising. For the large language model, I think not just the large language model, also the large, let's say the vision model, and so on, different multi-model. I think it is very promising to be integrated with CKM. For example, one possible integration that I can think of, and also I discussed with my group members, is that about the environmental description. A very simple description is that here we mentioned that if we want to build a CKM, we try to make use of the data. And another thing is that we try to specify the environment for the area that we want to build a CKM. Then maybe we can specify the environment based on the camera, based on, for example, by the point cloud. This is one aspect. Another aspect is based on the web or the language. Let's say we describe our environment. Let's say it's a dense environment, it's a city environment. We have a building here and so on and so forth. And also we can integrate this knowledge with the picture, with the point cloud. All this information will give us more concrete or more detailed information for the environment for us to build a CKM. I think this is one simple, superficial integration. Of course, we can have many other more in-depth integrations. For example, we can fine-tune the large language models, but I'm not sure whether we have sufficient data. And also, we can use some so-called RAG or build a certain database to retrieve the CKM. Some interactive. Of course, the large language model, the most beauty is that we can use an interactive interface to present our CKM and so on and so forth. Yeah, there are huge potentials, but yeah, I think there's still a lot to do, and many in-depth discussions and investigations need to be combined with the large language model or large vision models and so on. Yeah.
Okay, thanks. So the last question is related to a data set. Okay, so when we use AI, right, or large models, so we need to have good data set, right? So maybe you can have some brief introduction about data set. And a really related question is about retracing. So some people use retracing to generate a data set, and some people directly use retracing to generate the channel map, right? So if we have retracing, why do we still need a CKM, or whether we can use CKM and retracing to enhance each other? Yeah.
Yeah, thank you. Yeah, these are also quite important questions. For data set, yes, if you want to use AI, even do not use AI, but we also need to have a high quality data set. So if we try to build a CKM, as we mentioned just now, as a foundation model, we need to have a data set that have removed the impact of the transmitter or receiver. We only try to extract the environmental information, let's say the angle of arrival, angle of departure, delay for these particular locations. So that's why in this data set, we call it CKM ImageNet. So we try to mimic the ImageNet data set in computer vision. We add a CKM in front of ImageNet, a CKM ImageNet. We really try to build a data set that only depends on the environment. It is independent of the number of antennas. So in this case, we can build algorithms to support CKM construction. But of course, this data set, it includes angle of arrival, angle of departure for multipath, and also the delay. Basically, it is the CPM channel path information, channel path map that we try to build. But so far, we have released the data set in GitHub. I think if you search with this keyword, you can find it in GitHub and also in Hugging Face. And another key question, important question is that, yeah, we can use ray tracing to do the channel knowledge map, of course. And also, ray tracing, we have wireless insight, and also NVIDIA have the Siona to do the ray tracing with the GPU accelerated algorithms. But the key point is that if we can make use of ray tracing to do the channel knowledge map construction, that already means that we have sufficient specification of the environment to perform ray tracing. Let's say, for example, we need to know the accurate distribution of the buildings. We need to know the materials. We need to know the dielectric properties if we want to have a very accurate channel knowledge map construction. And another scenario is that requirement is that ray tracing is actually very time consuming. even with GPU or with very powerful GPU, if you want to use a ray tracing to do for example, city scale, it is very challenging, right? And another aspect is that, of course, we can use ray tracing if we know sufficient environmental information. We can combine this ray tracing result, as you mentioned, as a data set to help us to build the algorithms that will combine the data set from the ray tracing and also from the measurement, also from the environmental description, from the multimodal information to build a CKM. This kind of build of the CKM can be offline, right? Can be offline. Then when we infer this CKM, everything is already computed, and then we use just use the location information to query the CKM. That will be very efficient. You cannot expect to use ray tracing for every locations to do the real-time prediction. Maybe for 1 point or 2 points for a very small area, it is possible. But even with ray tracing, then we can make use of the ray tracing to build a CKM. A very clean CKM is a location specific, the mapping from a location Q to the channel knowledge. And then this data can be from the ray tracing result. And then in this case, we try to make use of this data to mix them up to get the efficient CKM construction and also inference. I think that is a key idea. Sometimes we need to do something offline, let's say ray tracing, and then the inference is online. Yeah.
Okay. Thank you very much, Yong, for the very insightful talk and very insightful answering. So I see we still have some questions. So we do not have time to answer all of them, but this is just the first lecture. So later we still have a lot of lectures. So I think for the audience, if you have any further questions, you can leave your question. I think maybe in the Taskbark website, right? You can leave your questions there, and the instructors will look at the comments and maybe try to address this question in the later lectures. Okay. So
Yeah.
thanks, Yong, again, and thanks all the audience, and maybe see you next week. Okay.
Yeah.
Bye.
Thank you, dear. Thank you very much.
Thank you. Thank you. Bye bye.
Bye.